Good morning, everyone. So, today we will continue with our discussion on stereoisomers with more than one chiral center. So, in the previous class, we drew the various stereoisomers possible for compounds with two chiral centers. And this was the particular example that we took in where we discussed the example of 2,3 butane diol. Okay, and we made four different stereoisomers that are possible for that compound on the basis of the formula that is 2 raised to the power n, where n is the number of stereocenter. So in 2,3 butane diol, the number of stereocenters are 2. So therefore 2 raised to the power 2, that means 4. So that many 4 stereoisomers we can draw for that particular molecule with 2 stereocenter, and these were the various stereoisomers that we drew for that particular compound. Now let us look. Now today what we are going to do is we are trying to relate these stereoisomers with each other and try to find out what is the relationship between them. So if you look, this we have discussed in the class itself. If you look these two, that is stereoisomers 1 and 2, their relationship is like they are mirror images of each other. So they are basically the enantiomers. They are basically the enantiomers. Same way, compound number 3 and compound number 4, they are mirror images of each other. So that means 3 and 4 are again, they are termed as enantiomers. Now, if you consider the relationship between 1 and 3 as well as 1 and 4, okay, they are not mirror images of each other. They are not mirror images of each other. Similarly, if you consider the relationship between the isomer 2 versus 3 or 2 versus 4, okay, they are not again mirror images of each other. So such stereoisomers which are not mirror images of each other, they are termed by another term called diastereomers. So if you want to define diastereomers, they are nothing but they are stereoisomers which are not mirror images of each other. Stereoisomers that are not mirror images of each other, they are termed as, what do you call as, diastereomers. So this is the new terminology you have to remember in this case. So when you draw the various stereoisomers, you will find some of the stereoisomers having the property of enantiomerism. Another relationship that you find among the stereoisomers is the property that they are diastereomers. That means they are not mirror images of each other. So such compounds which are not mirror images of each other, these two compounds would be diastereomers, these two compounds would be diastereomers, these two compounds would be diastereomers, 2 and 4 would be diastereomers. So such compounds where there is no relationship of mirror image, that would be called as diastereomers. So that terminology you have to keep in mind. So let me remove this now and let's move on with other discussion among these stereoisomers. Okay, now let us come to these two particular compounds, that is 3 and 4. So as we know, they are both enantiomers. That means they are mirror images of each other. Now, I told you in the previous class, in the case of Fisher formula, you can carry out two operations. Two operations are allowed. What are those two operations which are allowed? One is there can be two, if you do two interchanges of various groups and substituents on the chiral center, then it won't change the molecule. Or if you rotate by 180 degree in the writing plane. Okay, so in the writing plane, if you rotate the molecule in the writing plane by an angle of 180 degree, it won't affect the molecular property. That means it won't change the molecule. So that is what I'm going to show you here. So if you look at this particular thing here, if I am able to rotate this molecule by 180 degree across this axis, that is means this pen, the axis of this particular pen, the passing through the center of this molecule. So if I rotate this molecule in the plane by 180 degree, how it would look like? It would look something like this. So I'm turning by 180 degree. Suppose this is my cross here, and just to denote it differently, I'm putting like this. So when I rotate by 180 degree, this cross will come up and the square will come down. Okay. So now we have to arrange the grouping. So when I turn by 180 degree, H will all come in this side and OH will come in this side. Okay. So what I just now told is that if you do a 180 degree operation on any Fischer projection, it won't change the molecule. So that means fundamentally both these structures are structures of the same molecule. Now if you look at now this is same 4 stereoisomer is this is also 4 stereoisomers, only drawn as that I have drawn it in a different fashion, that's all. Okay, so now if you compare the 4th isomer with the 3rd, what do you see? They are perfectly the same thing. They are the same molecule. Okay, so here what do you see? They are not non-superimposable. They are not non-superimposable. If you remember, when we studied the property of optical isomerism, I told you if a molecule need to be optically active, it should show the property of chirality. Now in this case 3 and 4 are not chiral because the mirror image, that is mirror image of this is this one, and I just did an operation which doesn't change the molecule, but that molecule is superimposable of the original molecule, that is 3. So that means what? This 3 and 4 are optically inactive. Okay, you have to keep in mind that both these contain chiral centers, but still they are optically inactive. And that such type of stereoisomers, even though they contain chiral center but show optical inactivity, such type of compounds are called as meso compounds. These are called as, I'll write it again in a more clearer way, they are called as meso compounds. So how do you define meso compounds? These are stereoisomers which are optically inactive in spite of the presence of chiral center in them. Okay, so such type of compounds which are optically inactive, because even though there are chiral center present on it, those compounds are called as meso compounds. Now they can be defined in another way also. Such compounds will have a plane of symmetry in the molecule. What do you mean by plane of symmetry? If suppose you pass a mirror at the center of this particular molecule, what do you see? This part of the molecule would be the mirror image of this part of the molecule. So such mirror plane, if you are able to draw, so in this molecule also, what do you see? Same thing, it's a mirror image. Half of the molecule is the mirror image of the other half of the molecule. So you can define this meso compounds also as those compounds which have a plane of symmetry passing through the molecule, passing through the center of the molecule. So those compounds, stereoisomers, we don't say now onwards compounds, we will say specifically stereoisomers. So those stereoisomers which contain the plane of symmetry are called as meso compounds. So meso compounds are what? Optically inactive, because their mirror image is superimposable on its original molecule. So this term, we have learned 3 particular terms in today's class. One is enantiomers, which we already discussed before. Then we discussed diastereomers, and then we discussed meso compounds. So keep these terminologies in your mind. In the live sessions, I'll be discussing on the example of two molecules which is in your syllabus, that is lactic acid. Another one is tartaric acid. So please be prepared, but try to understand what all terminologies I discussed in here, and we will discuss them in the coming class. Thank you very much for your attention.